In this section, we're going to start taking a look at non-homogeneous differential equations of second order. And remember, non-homogeneous means that it's equal to some function g of x as opposed to the zero. In the last section, we were able to solve the homogeneous type. All of the ones that we're going to be looking at are going to have at least a variable or a non-variable coefficient, a constant coefficient in front of the y prime. All right. So if we go through and try to solve this, then there's going to be actually two solutions. There's going to be something called the complementary solution, and there's going to be a particular solution. The complementary solution is when the second order differential is equal to 0. So essentially, what you'll have is you'll have 0 plus something called the particular solution. The particular solution is the solution that satisfies the right-hand side. So for example, let's say we have a really basic non-homogeneous. So let's say y double prime plus 3y prime plus 2y is going to be equal to 3x plus 5. That would be true that it would be 3x plus 5 plus 0. So you're trying to find a y so that when you substitute it back into the three derivatives, it would give you 3x plus 5. That's the yp. The yc is the solution that's going to be equal to 0 when you substitute back in. So in essence, everything that we've already done so far with second order differentials, that's going to be done in every single type of problem that we go forth with these second order differentials, at least when we solve it using constant coefficients. Now the question is, we already know how to solve yc. That's what we just did in the previous section. However, yp, using this method undetermined coefficients, we're going to guess a solution. And to guess a solution, we're just going to have to know what the forms look like. And here's the different forms, at least some of the more simplistic ones. So for instance, if it's a polynomial, let's say you have a cubic, then you just set it equal to ax cubed plus bx squared plus cx plus d. Even though there's no x term, a derivative of that cx term might actually help to solve the differential. And then we have some transcendental functions. So for instance, if we had something like e to the minus 3x sine 5x, then remember, when you take successive derivatives of sine, you also get a cosine in there. So the solution, or the guess, would be ae to the minus 3x, because that's not going to change no matter what. And then the sine is going to toggle between sine and cosine. So my advice to you would be to memorize this table to get the general forms down as quickly as you can. That's going to help you to be able to guess what those solutions are going to be. So essentially, if we're solving this, the first thing that we do is we find yc. The second thing we do is we guess a solution. And then the third thing we do is we find yp. And yp is going to be the guess. And you're going to substitute y prime of p, y double prime of p, etc. back into the differential to determine whether or not your guess is correct, and then to solve for the undetermined coefficients. Okay, so the goal is to solve for a, b, c, d, etc. All right, it's not that difficult. Most students do really well with this. So I do want to illustrate a couple examples of non-repeated solutions. Now, when we do get to repeated solutions, that's where it's going to start to get a little bit dicey. So, but I'll show you how to work those. Let's start off with a really basic example. 4y double prime plus 9y is equal to 15. So, first thing we do is we find yc. And yc, all we're going to do is we're going to find the complementary solution by setting up the auxiliary equation. So that's 4m squared plus 9 is equal to 0. So ignore the 15 for right now. We know that to be able to get this solution, m squared is going to be equal to negative 9/4. Or m is going to be equal to plus or minus, if we take the square root of both sides, that's going to be 3/2 I. And so what we have is that we have a case 3, where a is equal to 0 and b is equal to 3/2. And so we can say that the complementary solution, YC, is going to be equal to e to the 0x times c sub 1 cos of 3/2 x plus c sub 2 sine of 3/2 x. And this is old stuff. We already know how to do this. All right. Now remember, e to the 0x is 1, so we really just wind up with the complementary solution being c1 cos 2x, or 3/2 x, excuse me, plus c2 sine 3/2 x. Now we're going to do the new stuff. We're going to find the particular solution. Now the particular solution says that we look at the right-hand side. It's a constant. So we go back up to the table, and we're just going to set that equal to a, because it is a constant. Okay, so anytime that the right-hand side is a constant, just set that equal to a. So we're going to guess that yp is equal to a. Now we notice that in the differential, we need a second derivative. And that's really easy because the first derivative of a constant a is 0. And we know the second derivative is 0. And so what we're going to do is we are going to substitute those back into this equation. Right? So remember, y double prime, or 4y double prime, plus 9y is equal to 15. We know that y double prime is 0, and y is going to be a. So we get 4 times 0 plus 9a equals 15, and that means that a is 15/9 or 5/3. Right? And so that means that our solution that we're going to get, which I'm going to call y at x, is going to be equal to the complementary plus the particular, which is going to be equal to, remember that c1 cos 3/2 x plus c2 sine 3/2 x, and then plus the 5/3. Right? Now, of course, if you don't trust the answer, then what you do is you just go ahead and find the second derivative and substitute it back in. Right? In this case, I did check this beforehand, and that is indeed the correct solution. Now remember, when you substitute this stuff back in, the c1 and c2 cos and sine, that equals 0 when you substitute. So really, in the original differential, you have a plus 0 up there. Let me show you a second example. This time a little bit tougher, but not too bad. So we have 1/4 y double prime plus y prime plus y is going to be equal to x squared plus 2x. All right, so start by finding the complementary solution, and that's going to be 1/4 m squared plus m plus 1 is equal to 0, or m squared plus 4m plus 4 is equal to 0 by multiplying by 4. We can factor that into m plus 2 squared is equal to 0, and this gives us a double root. Okay, so it's actually a case 2 because we have a multiplicity of 2 going on here. So the complementary solution, I'm going to call that YC, and see if you can remember how to do this. All right, C1e to the minus 2x, and then remember you just multiply by a factor of x, so C2x e to the minus 2x. And let's hold on to this. Okay, so we need this when we go to find the general solution in total. Now YP, we need a guess. We look back up, we see that we have a quadratic that it's equal to. So a quadratic has the form ax squared plus bx plus c. Notice that we have a second derivative and we have a first derivative. So we're going to have to find y prime of c and y double prime of p. Excuse me, y prime of p and y double prime of p. And both of those are easy. The derivative of ax squared 2ax. The derivative of bx is b. The derivative of c, nothing. The second derivative, so the derivative of 2ax is 2a. The derivative of b is nothing. We're going to substitute that back into the original 1/4 y double prime plus y prime plus y equals x squared minus 2x. Right? And so if we do that, 1/4 times 2a, because that's y double prime, plus y prime, which is 2ax plus b, y double prime, and then finally plus y, which is ax squared plus bx plus c, and that's going to be equal to x squared minus 2x. All right, so now's where it gets a little bit dicey for us. And when I say dicey, I mean a little bit more algebraically taxing, although not too terrible. All right, I'm going to rewrite this. All right, so we're going to have 1/2 a plus 2ax plus b plus ax squared plus bx plus c equals x squared minus 2x. And what I'm going to do is I'm going to group the terms that have like powers of x. All right, so anything with an x square, I'm going to write by itself. All right, so we have this ax squared, and all the way over here we have an x squared. Right. And I'm putting these in different colors on purpose, and you'll see why in a moment. We're going to put anything with an x together. All right, so we have 2ax and we have a bx. All right, and over here we have minus 2x. And then anything with a constant in it, that's going to get its own variable, or I'm sorry, that's going to get its own color as well. So notice that we have 1/2 a, we have b, and we have c. So we're going to say 1/2 a plus b plus c. All right. Now technically on the right hand side there is no constant. And what I want you to notice is that this is really a system of equations. And here's how. The coefficient of x squared has to be equal to the coefficient of x squared. The coefficients of x have to be equal to the coefficient of x, because this is an equation. An equation has to be balanced. And then the constants have to be equal to the constant. And so here's our system of equations. All right, and I'm going to write this in different colors so that way we understand how it's going. Not to oversimplify it, but just to make sure everybody understands. So our first equation, we're not going to worry about the x, is that a is going to be equal to 1. Coefficient equal coefficient. The second equation, 2a plus b is going to be equal to negative 2. So we have a 2a, we have a b, and that's negative 2. And then finally, we have some constants. We have 1/2 a plus b plus c is equal to 0. All right, that's the beauty of the undetermined coefficients method, is that when it comes down to it, it just boils down to algebra after you've substituted those derivatives for yp. All right, now, easy enough. A is equal to 1. All right. 2 times 1 plus b is negative 2. All right, so we just substitute back in. So we have 2 times 1 plus b equals negative 2, and that means that b is negative 4. Right? And then finally we substitute back in down here, so we have half of 1 plus negative 4 plus c is 0, and I believe that's going to give us that c is going to be 7/2. By adding these two together, that gives us a negative 7/2, and then we add it to both sides. And so we're done now, because the particular solution, we just substitute a, b, and c back in. So yp, remember that was ax squared plus bx plus c, which is going to be equal to 1x squared minus 4x plus 7/2. And then finally, for the final solution, y of x, which is equal to yc plus yp. Remember, yc was c sub 1 e to the minus 2x plus c sub 2 x e to the minus 2x. All right, remember all the way back about 7 or 8 minutes ago, we found the complementary solution. And then we're just going to add to that the particular solution, which is going to be x squared minus 4x plus 7/2. All right, so these were two examples of polynomial types. Okay, polynomials are really easy types. When we start looking at the transcendental types, that's where it's going to get a little bit tougher. Okay, so for right now, just make sure you're confident with this process before you move on, so that way we can start doing other types of systems.